Welcome to EDU World Space.
Alright, in this problem, we are given a suspension bridge, in which case the cables are subjected to a uniformly distributed load. They want us to find the maximum distributed load in pounds per feet, given that the tension in the cables is capable of sustaining a maximum tension of 3,000 pounds. For this particular problem, there are three equations that we need to consider. The first one being the equation that is used to determine the curve of the cable, which is defined by y equals 1 over f sub h times the double integral of the distributed load. F sub h represents the horizontal component of the tensile force at any point along the cable. We also need to consider the equation of t times cosine theta equals f sub h, as well as tangent theta equals dy dx. Now, before I start solving this problem, I first want to establish the origin of coordinates for the cable, which in this case will be directly at the center or in the middle. And the reason I do this is because of symmetry. And you'll also see why I needed to establish these coordinates as we get further into this problem. Now, the first thing that we want to do in order to solve this problem, we need to start by deriving the curve of the cable using the first equation that was written on the board. Now, because the distributed load is supposed to be a function of x, and because we do not have one, we can simply replace w of x with w because it's given in the problem right there. So if we replace w of x with x, and we therefore take the first integral, our equation then becomes y equals 1 over f sub h times the integral of wx plus c1 dx. And the reason we have c1, which in this case is a constant, is because we aren't evaluating any of these integrals with numerical values. So therefore we need these constant variables. Now if we take the second integral, our equation for the curve becomes 1 over f sub h times w times x squared over 2 plus c1x plus c2. Now that we have this equation, we can't necessarily do anything with this simply because we have constant variables in our function and we have to solve for those. So in order to solve for c1 and c2, we have to use boundary constraints. And in this case, our boundary constraints will be y equals 0 when x equals 0 for the original equation. And when you take the derivative of that equation, dy dx, will still be 0 again when x equals 0. Now, the only way I was able to establish these boundary constraints is by first setting up the origin of coordinates as I did in the beginning of the problem. So now that we have these, and once you plug in the constraints for the original equation and you plug the constraints in for the first derivative of the equation, your final equation, your final equation will then become y equals 1 over f sub h times w x squared all over 2. Now we're going to use this equation in order to solve for f sub h using the appropriate x and y values given in the problem. The y value that we're going to use is 6 feet. The reason we use 6 feet is because it was given in the problem. And the x value that we're going to use is 25 feet. The reason we use 25 feet is because our origin is directly at the center of this cable. Now, the whole length of this cable is 50 feet, but once we put our origin directly in the middle of that, and we measure from that point to the far right end, it's 25 feet. Now, if we plug in these values, we get f sub h equals 52.08 feet times w. So now that we have equations A and B, we are going to set aside equation B for now, and we are going to solve for the maximum angle using the equation of tangent theta equals dy dx. Now dy dx, as you should know, is y prime. We solved for the equation of y in equation A, which is right here. Now if we take the derivative of that and set that equal to tangent theta, we get that tangent theta equals wx times f sub h. Now we know what f sub h is because we solved for it above. Now if we plug in, or we substitute in f sub h, tangent theta then becomes wx times 52.08 feet times w. Substitute this in right there. Now as you can see, we have like terms and we can do some canceling. So we're going to cancel out w. And I also forgot to mention that we are going to evaluate this at x equals 25. Why are we evaluating it at x equals 25? Again, because our origin is at the center of the cable and we're measuring from that point to the far end of the cable, which in this case is 25 feet. So if we plug in 25 feet, 25 feet all over 52.08 feet, that leaves us with tangent theta that leaves us with tangent theta equals 0.480, which therefore allows us to solve for theta. So theta equals the inverse of tangent of 0.480, and the maximum angle in this case is 25.64 degrees. Now that we have our angle, our maximum angle, we can finally solve for f of h using the equation t times cosine theta equals f of h. We'll solve for f of h, which will then lead us to solve for the distributed load. So we know that T in this case, the maximum tension is 3,000 pounds. So we have 3,000 pounds times cosine theta, what we saw for up above, which is 25.64 degrees, equals F sub h. When you evaluate that, you get 2,000. Let's write that again. You get 2,704.59 pounds. Now, remember earlier that we solved for f of h right here next to this b. This b right here. We said f of h equals 52.08 feet times w. We solved for f of h. We substitute that numerical value in for f of h, which will give us the distributed load. So we'll go ahead and finish off the problem by saying that the distributed load, W, is equal to f of h, 2,704.59 pounds, divided by 52.08 feet, which equals 51.93 pounds per feet. And that is exactly how you solve this particular problem. I hope that helped.